Welcome everybody to this weekly meeting in quantum mobile networking. Today we have finally our first presentation from the Federal University of Pará and the Technical University of Dresden. Two speakers are Felipe Bastos and Shima Hassanpour, who are here today. For the participant, you should be able to see the slides. Both I send them as an attachment in a reminder. And I also, for who has access to Ilias, you should be able to see them in the web platform. So as usual, the presentation will last roughly 30 minutes and it will be followed up by a 15-minute question and answer session. For those students who need ECTS or want to take this course somehow formally, or they need recognition from universities and so on, I posted in the chat two links. One is an evaluation form, which contains a couple of scoring metrics for the presentation. This is more to train your somehow critical skills. And then there is a set of questions in the folder exercise in Ilias that you also need to answer by the deadline you find in Ilias. Is a set of 3 questions that have been produced by the speakers. So before moving on to the presentation, I would like just to remind, if you have questions from the students, you can either write them in the chat, and then we will handle them at the end of the presentation, or you can just ask them directly at the end of the presentation. So before starting, I would like to ask the other groups if they have started interacting, how the collaboration is going, if you faced any roadblocks, or how can we help you to improve your collaboration. So any feedback from the other groups? Everything going smoothly? Okay, so it looks like so. So if you have any issue, don't forget, you can always reach out to us and send us an email or the Ilias forum. We are here to support you. So this said, we can, I guess we are ready to start the presentation. So who is going to share the screen, Shima or Felipe?
Shima, can you share the slides?
So our presentation is about the physical implementation of quantum channels in quantum mobile networks. Here is the outline of our presentation that I actually present and talk about the motivation, quantum information, quantum channel, and also Felipe will present the quantum channels in practice. So what is the motivation actually to move from the classical communication to the quantum communication? The most important motivation and the reason is that quantum communication has the potential to achieve unconditional security. It is undoubtedly true that the most crypto systems, such as RSA and deep Pullman key exchange method, in principle, they can be broken because they are computationally secure. It means that they actually can be broken and by the ability of solving such computational hard problems. And for example, the security of the best known crypto system, such as RSA, is based on difficulty for factoring large integers. And in 1994, Peter Shor invented an efficient quantum algorithm for factorization. So if a large-scale quantum computer is constructed, much of conventional cryptography goes far apart. And there are 2 approaches to a quantum-safe crypto system. One is post-quantum cryptography, and the other is quantum cryptography. that is basically is information theoretically secure. So what is quantum communication? Quantum communication is the act of transferring a quantum state from one place to another. And in a generic form, quantum communication consists of 3 steps. The first step is the preparation of the quantum states, in which the classical information is encoded to the quantum space. If the classical information encode to the single qubit, such as the polarization of the state, we call this as a discrete variable, and if it is encoded by the quadrature of a signal, we call this such as a continuous variable. And we have another step for transmitting these quantum states through the quantum channel. And inside the receiver, we have such as the coding and detection. That for the discrete variable, we have a single photon detection, and for the continuous variable, we have such as the heterodyne or homodyne detection. There are 3 important fundamental and characteristics of qubits, such as the superposition of the qubit, that it can be in a superposition of 0 and 1. And the next feature is that it cannot be copied without disturbing the qubit or modifying the information. And the third one is that the qubit cannot be entangled, can be entangled to one another. It means that if we measure one particle, the other particle will automatically collapse, and there is no counterpart of entanglement in classical scenario. So by this important feature, it allows us to present a new form of communication. So for the quantum channel, we have one option for sending quantum states through the quantum channel, is that using such as a ground-based optical fiber. And in fact, fiber actually affected through the optical attenuation and polarization problems. We have such as a limitation for the distance. And one solution is to introduce such as a quantum repeater. And the other limitation for the fiber, we can talk about the losses, that it is exponentially increased by the distance. And we can actually move to a free space optical channel that they are more feasible in infrastructure. And the other option is could be a microwave channel. That the motivation of applying such this channel nowadays is that to have a secure communication between remote superconducting circuit that they are based on the microwave frequency that between 1 to 10 gigahertz. Now we have the entanglement swapping feature that it says that this method can entangle 2 particles which have never interacted. And if we have 2 EPR pairs, that particle 1 and 2 are entangled together, and then we have another EPR pair that particle 3 and 4 are entangled together. So if we have, if the sender has particle 1 and 4, and the receiver has particle 2 and 3 under positions, and if a sender make a Bell state measurement on her particle, the states collapse and the receiver's particles become entangled to each other. So this feature is applied inside the quantum repeater, that if we have 2 remote nodes that each node send half of their particles to the intermediate nodes. And if the intermediate nodes that we call this a quantum repeater apply such as Bell measurement, so these two remote nodes become entangled via the Langer link. Now I want to define what does the security mean in quantum cryptography, in quantum protocols. Also, it is not true that most cryptography and all cryptography are perfectly secure, and each protocol define parameter that quantify the security of this whole scheme. And we can define such a hypothetical game for defining such this parameter when we define such a distinguisher that has a black boxes that it interacts with an unknown system, and then it will be asked to reply such a question that whether it interacts to the real or ideal scenario. So in this case, we define such a distinguishing advantages that it is the difference of probability that he can say that, okay, in this scenario, the distinguisher interact with the real or ideal one. And with this definition, we define a parameter that if it is small, so we say that the protocol considered secure. And now we can parameterize such the protocol by this parameter. And the security also relies on the assumption about the physics of the device. And for most cryptography schemes, such as QKD, there are three main assumptions. The first assumption is that they also assume that all devices are correctly and completely described by the quantum theory. It means that the adversary is limited by the laws of quantum theory. And the second one is that the classical channel is authentic. It means that an eavesdropper can listen to the channel without modifying it. And the third assumption is that the device do exactly what they are instructed to do. However, experimental of implementing such as protocol show that it is failed this assumption. And we can also assume that such as eavesdropper or Eve also just can store classical data. That by this way we define the security of the protocol against defined individual attack, or more generally we can improve the security against a collective attack. And in practice, imperfections actually in the experimental setup create side channel attack that can be employed by an eavesdropper. And we define such as the active attacks, such as the Trojan horse attack. It means that in the setup, when we have such a transmitter and receiver, so an eavesdropper send a bright light to the transmitter or to the receiver unit, and by the reflected back of the signal, he can find out the phase modulation of the signal, and he can extract the information or break the key and break the security of the channel. And also we can define such as passive attacks, such as the power attack, that it is related to the power consumption about the devices in the experimental setup. Okay, it is my presentation, and then Felipe continue to the quantum communication in practice.
Yes,
scientific hypothesis makes is illustrated here in
Shima, can you continue showing the slides for me so I can present, please? So in this part of the presentation, we are going to talk about real implemented test beds using quantum channels in practice. So we are going to talk about how today's the real experiments are being doing, and we are also going to talk about some future ideas for quantum channels implementation. Can you go to the next slide?
If you want, you can also download the presentation from the chat and also share it if it's easier for you, but as you prefer.
Okay, that's fine. So the most quantum communication hardware that are implemented today in the majority of these experiments and test beds that we have in the literature using light as a channel for the transmission of quantum information over a quantum network. And here we have an example of a hardware implementation of a quantum communication link. So maybe the communication are joined by lasers that propagates the light, and they also have a pump laser. There is a part of the system that is responsible to increase the energy level of an atom, so it's possible to work with single photons. So this increasement in the energy level it's needed to change the modulation, the phase of a single photon, and the transmitter can send the information, and with some special plates, it can change the polarization of a single photon and sending to the receiver that can read also the single photons and get back the information on the receiver side. Can you pass the slide, please? And also, the systems are normally coupled in optical fibers. There's the material that can conduct the light from one node to another, so it's possible to send the light signals easily in the system. And it's also the optical fiber. It's also a good option because it is already implemented for classical systems, and there are also works like the work where I got this picture that I use the physical infrastructure that are already implemented to also send quantum, to also provide a classical and quantum channels. But as Shima previously discussed, the attenuation can be a problem in optical fiber. So for worldwide communication, a possible solution is the use of satellites. Can you go for the next, please? So another interesting implementation of quantum communication, already also using light for doing this kind of communication, is the use of satellites. Also because as we need using light in communication, we need to have a direct pointed laser, it's easier to use satellites to communication between large distance. So it's possible to have a lot of ground stations, and so it's possible to point a laser to a satellite that is in the orbit, and it's possible to send the quantum information for another satellite and distribute to other ground stations. Here we have an illustration of the Meteus system that is that was implemented in China, where they have already done a lot of experiments changing information between different ground stations, also in China and also between China and Australia. So the use of satellites enables the possibility to change information using quantum channels between two continents. Can you go to the next slide, please? So, and also for UAVs can be used to increase the performance of the systems, as it's possible to use a swarm of UAVs to get the signals from the satellites and distribute to ground station in a way that to avoid noise between the communication links. Can you go to the next slide, please? Here, we are going to talk about an experiment using two UAVs to send information between two ground stations. This is a real test bed that was implemented also in China, where they embedded into two UAVs and two drones the transmitter and receivers using the hardware that we saw in for this real test bed. They embedded into two drones, two UAVs, with quantum receivers and transmitters that using lasers to change information between two ground stations. Can you go to the next, please? And so in this experiment, they arrived to change information using the help of three UAVs. Here we have the transmitter that is a ground station that is sending information for one UAV here. And this first UAV receives the information and sends to another UAV, to the drone 2, and that is also receive and sends the information to the final receiver that is another ground station. And the performance this experiment for 2 minutes, sending quantum information between the initial transmitter and the final receiver using lasers. And the initial transmitter and the final receivers are separated by a distance of 1 kilometer. And here we have the CH-SH correlation of the reception. And the authors of this study concluded that it's possible to change quantum information securely between the two nodes with 1 kilometer distance with the help of UAVs. And in the future, it will also be possible to integrate the UAVs with the satellites to amplify the range of the communication link. Can you go to the next slide, please? And also for the future, there are some experiments regarding the use of single particle, single photons in microwave channels, but they are very experimental studies that are focusing on reading and writing information in single particles using microwave, there is no real test bed for quantum communication using microwave yet, but there are some works that already describes how quantum networks using microwaves will look like in features. So here we have an idealized structure of a local area network where some ground stations can communication with light using quantum links, quantum channel satellites. Now, so in the ground, it's possible to have some microwave transmitter changing information with the final nodes, and also ensuring a link with classical networks for this local area quantum networks. Can you go to the next slide, please? And besides all those advantages that we can see that we have already quantum channels and networks implemented in practical in some experiments, but we also have some limitations, like as the communication are normally based on single particles on single photons. We lose a particle, we lose all the information, so it's not possible to reconstruct the package. Normally in classical networks, to avoid losses, we can send twice the same information to ensure the reception, but as we discussed here, for quantum information, it's not possible to copy and replicate the qubits. So we only can send a qubit once a time. So it's a huge problem for quantum channels, because for quantum communications, because you have this limitation. But it's in the second limitation here of the list. It's important to note, if we are working with classical information, but in quantum networks, we can replicate the informations as we do in classical networks. But when we are dealing with quantum bits, with qubits, it's not possible to send again twice or more times the same information. And if we lose a particle during the transmission, it's not possible to recover. So it limits the capacity of the quantum channels, in fact, when we are using quantum information. And the real test bed that we have in the literature are also experiments with just one or two transmitter and receivers. We do not have already tested with a large number of users as we have today in classical networks. And also when we are using optical fiber that are the most used physical infrastructure, we have this limitation of distance. Can you go to the next? So here, and we did this summary of everything that was implemented, and also discussed the limitations that we have today. That's it. Thank you.
Thank you so much for your presentation. Very good presentation. So now we could open the question and answer session. So is there any questions for the presenters from the audience?
So through all your presentation, the idea of exchanging communication. So the point is, what do you mean by quantum communication? What will be so? Because I think in one of the first slides, you said that. Slide 6, you show that there is some input classical information which encodes quantum states. So is this really what you mean by quantum states or quantum communication?
Okay, your question is that the way of encoding such the classical information to the quantum states, or another.
So yeah, so for it's the slide 6 is not, let's say, completely, because it looks as the quantum channel only encodes at the beginning. You have like input classical information, but quantum information cannot be fully reduced to a classical information, to a set of classical information. So if you have a quantum state, so the idea of quantum communication is, as you mentioned, so maybe a second question, and then we'll talk. So you mentioned quantum communication is useful for security, for quantum cryptography or quantum key distribution. But what could be another application of quantum communication? So what would it be good to transfer quantum state from one location to the other?
Okay, you mean that without sending the quantum state? I mean that another idea is such as the teleportation. Yes, that the quantum state is teleported to a remote distance.
Yeah, but the question is just more generally, what is the usefulness of transmitting quantum states from A to B? Cool. Okay, maybe, okay, if I give you some hints, so if you think of, now we don't have yet very efficient ones, but there may be in the future some good quantum computers. So, and if you think, so the internal register of a quantum computer when it is performing a computation is a quantum state. So it cannot be, so if you would like to connect, to perform some quantum computation between remotely distributed quantum computer, then what would you need?
You mean that without sending, okay, we need a pre-shared we need a pre-shared resources to sending a quantum state to one place to another. So for the communication channel, for the quantum communication channel, we need a pre-shared, such as the entanglement distribution.
Okay. So entanglement distribution actually is quantum communication. So the idea is, so any protocols that distribute quantum state, including entangled states, is quantum communication. So exactly. So if you have shared entanglement between quantum computer, then you can have some kind of shared or distributed quantum computing protocols. And in order to share those entangled states between the computer, then you need some quantum communication schemes. So just as a remark, so according to that, so it's as I was mentioning, so also sharing entanglement is, and actually most of the experiments you showed in the second part, they're related to sharing entanglement. So as from the satellite or even in the drone experiments. So it's not only that a quantum state is sent from A to B, but it was in those cases that on one of the drone or in the satellite, there is a source of entangled states, and the two parts of the entangled states are distributed to two partners, two nodes, so to say, of the network. So just to mention, so really quantum communication is not only about sending from A to B, let's say a quantum state, but it's also more generally, so distributing entangled states. So if I can let the question for someone else, if there are some questions.
Yes, thank you. So yes, Nabil after Maur.
Yes, thank you first for the presentation. It was really nice. My question is about slide 8, which you have open right now. But there was one more point about the microwave channels. So as I understood it, you provided it as an alternative, but my question was, I was not really sure, was it as an alternative, or is it also possible to transmit quantum states over a microwave channel?
Yes, there's also actually the quantum channel could be a semi-rigid, such as a cable that they use for sending such the quantum state through this cable.
Okay, that's very interesting. Yeah. Thank you.
Yes, more questions?
Yes, sir, can you hear me?
Yeah, Alexander.
Yeah, I just tried to ask before, but something is with microphone, sorry. So the question is the next thing. Due to the fact that basically even classical networks are built from the host, some sort of bridges like routers and switches, and the intermedium, and in quantum networks, we will just misplace the intermedium and maybe the routing stuff, a question arises. How do you think will eventually the quantum communications will be combined with classical protocols we use today, or will it be born with a completely new type of things? Because currently, even in the terminology used in this presentation, like QLAN, quantum local access networks, we are basically relying on the same schemes, but we're just using a better technology as an intermediate. Thank you.
Yeah, as we can also define such the hybrid quantum to classical network.
Sorry, again?
So you mean that there is also a possibility to define, as we have such the classical or quantum era, so we can define such a hybrid classical and quantum network.
Yes, but usually it just includes the coordination of classical and quantum devices, which is obvious for at least today's use. But my question was rather about the protocols and the logical base of the quantum computing and quantum networking. So it's just your opinion. How do you think? Will it eventually quantum principles displace the classical view of networks completely, or will it combine the logics from both sides?
No, I think it's actually relative on both sides.
Okay, thank you.
Thanks. More questions?
I have a question.
Yes, Pratik.
So you mentioned about quantum hacking. How would that work? Like, my idea was that since we are using teleportation, it is not that easy to for any other person to like have an attacking done. So like how does that work? Is it more about sending qubits from one location to the other, or is it the attack happening on the, like, when teleportation is happening?
So the most implementation, it was actually about the implementation of QKD, quantum key distribution, and they actually demonstrated such as attacks in these setups.
Can you elaborate on that? Like what? Like, can you give an example in terms of what kind of attacks are we talking about in QKD, or what sort of protocols?
Yeah, in the BB84 protocol, or some in ECART 1991 also.
I see. Thank you.
Okay, thanks. Do we have more questions? We still have a few minutes.
I have a question for Stefan.
Yes.
Like he explained while answering to Shima, he explained that we cannot replicate the quantum information completely. because when I was reading some text, I knew that like using 2 to the power n cross 2 to the power n matrix representation, you can actually encode quantum state. So can he, did I hear him wrong, or like he can explain this in a more better way, I guess?
So your question was about the capacity to duplicate the quantum states.
Yeah,
so
true.
This is all based on the fact that when you perform a measurement on a single quantum state, the output of the measurement is random, essentially. So which means you can see that as the fact that if I give you a given quantum state, I may know it, but I've prepared it, but then I give it to you, you don't know it. So there's no way for you to know which quantum state is it. So I said, because you can only perform a single measurement on it, so to say, and then depending on which kind of measurement you do, you will get some random results. And if we repeat the experiment, you can have another result. So essentially, if you only have one-shot experiment, you will not be able to tell me exactly what was the quantum state. So then maybe you can give it, so you can tell with some given probability what it is or something like this. And of course, if you want to know the quantum state, you have to repeat the measurements many times to make kind of tomographic, and then you know if you have many copies of them. So because you cannot do that, so you can see that, so then you cannot copy, because the spy who would like to copy has to measure the state, and then by doing that, it will destroy it.
Nice to hear, because I was not thinking in the way of Copenhagen interpretation. I was thinking like probabilistically you can assume what was the initial quantum state. If you at least prepare the mini quantum state, do similar type of operations and get the measurement, then probabilistically you can determine.
So,
if you
of course, you're right. If you have many copies of the same quantum states, then you can. But if you have only one copy, and this is how its quantum K distribution is based, you only have one copy. And so the spy can only get some limited information about the states. So that's the, and in addition, it will perturb the state if the spy makes some kind of intercept and recent attack. And so this perturbation will then be tracked down into the protocol later on.
Also, I have a continuing question from this. Like while we are doing the POBM or like measurement, how we are sure about the basis? So we created a quantum state in some particular basis, and the devices in which we are measuring the quantum states can have some different basis. Right now, we are assuming that the initial the measurement basis is completely deterministic. How can we relate it with the initial conditions?
Well, actually, so when you prepare the quantum states, of course, if you do it actively, so you need to select some basis to describe it when you prepare it. But once the quantum state is there, so actually the basis, they are not related to the quantum state. So the quantum state is a vector in a Hilbert space, so in a vectorial space. And the vector exists by itself without, if you have a vector in space, it doesn't depend on the choice of the reference system you choose. So the vector is always there.
Here I will contrast, like it can be depending on the superposition of both the states. For example, I had a ground or excited states, then our quantum state,
Yeah, you're right. If you're 0 plus 1, you have select, but then it means you started by choosing the basis 0 and the 0 and 1 as a specific basis, but you could have taken any other one. So actually, once you prepare the state, so of course, and okay, again, if I come back to the example of quantum cryptography, so it's really the fact that Alice has to select between two bases. And Bob has also to select between two bases, and it's only when they choose the same basis then they have perfect correlation between their bits. Whereas if the bases are not the same, then they have no correlation at all. So So I'm a bit lost now
No.
with your question, but it's,
yeah, my question was at this junction point, like if I interact with the system, if I created a basis and I interact with the system, I got the measurement results and I lost the system. But how can we be 100% sure that like the basis which we created, like 0 or 1 to measure the system, was similar to the initial setup, the initial basis from which the quantum state was even prepared?
Yeah, but, okay, maybe that's good. So, what do you mean by choosing the basis for the preparation? So to say,
the particular 0 or 1 state, or
exactly. So which means, so if you at the preparation stage you select only 0 or 1. This is what you say.
Yeah.
Oh, exactly. So, but then if you do it like this and you give that information public, then it's classical information or communication, if you want, because then you just send bit 0 or bit 1, and the receiver, knowing that you have selected the basis 0, 1, will always measure in that basis, and then you have a classical scheme, so to say, of communication. You send 0 and the receiver receives 0, you send 1, the receiver sends 1. So it's really the fact that for instance, the emitted states are in a superposition state, which makes the quantumness, because if you send 0 plus 1, then you have 50% of getting 0 or 1. I would say, so it is really coming back. It's it's the key of quantum cryptography, that exactly the basis on the measurement do not correspond as in the basis, so to say, on the emissions or so on. And this is why it's working, why you have quantum effects. Otherwise, you would have no quantum effects. So, and you will not be able either to detect entanglements or make teleportation or such protocols. So it's all based on the superposition. You need to have those states in a superposition.
Okay, thank you. Thank you for the explanation.
Thanks. We have time for maybe one last question from the audience.
Hi, so I have a question.
Yes, Giuseppe.
Oh, thank you. Maybe it's repetitive, but in slide 7, it's written that the qubit cannot be copied without modifying it. Okay.
Mm-hmm.
So is hacking limited to a few type of attacks?
You actually, when it is modifying the information, is basically is that when you measure the qubit, so the result is classic, and then you cannot do anything else with this qubit. So you disturb this qubit. So when you have such an eavesdropper inside the quantum channel, so when she measures this qubit, and then she has to prepare another state. So by the chance, when, for example, if we talk about the QKD protocol, so the eavesdropper have 1/2 probability to distinguish that it is in the Z or X spaces.
Okay. Thank you.
Thanks. So I guess, are there more questions? Okay. So maybe I have really one final question regarding the difficulty of creating a microwave channel. So could you expand a bit more why, might be trivial, but why is it more complicated to establish a channel over with microwave than an optical channel?
I think that the most important factor is that the use of microwave for quantum communication is something that is very recent, because we didn't need it before. So it's something that the studies are coming up in now. So, and the communication based on light, it's something that is have been more discussed before. And So we have initial experiments using microwaves. There is very recent studies. So I think this is the main factor that we don't have test beds using microwaves today.
Thanks. And is there maybe some additional, like a physical aspect, for example, related to the frequency of the wave or the energy of the particle, something like this? What about, is there an effect called decoherence or things like this? Could you expand on that?
Yes, I think also to have equipment on the manipulation of single particles using this frequency is something that's not very trivial also. So, and it's also another limitation.
I have a follow-up question from this. I saw recently a paper from National University of Singapore that they were able to perform microwave to optical conversion, basically. So I guess these things can be very powerful and important tool in this type of communication, where you can convert the microwave signal to optical quantum states and then use the optical operations you want to perform.
That's great. Could you share this paper with the seminar participants, with everybody, or on the forum? That would be very interesting for everybody.
I will send.
Yeah, thank you so much.
Thank you.
Okay, so I think we have run out of time. We have 1 minute left of our hour. So first of all, I would like to thank everybody for the really amazing event and the organization, and from the speakers, also the really fantastic and insightful questions and the answers. So I'm really happy of how the first meeting of our series turned out. So now we will meet next week with the second group, and the topic will be about simulation tools for quantum mobile networking. Are the people of the group here connected? Did you have chance to interact? How is it going?
So far so good. I'm lucky with my group, so yeah, everything is fine right now.
And what about the group number 2? I think here we have Tyreen is connected, and who else is the member of the second group?
I'm also the member of second group.
We
are in contact.
Okay, that's great. So things are going smoothly, I hope. Okay, so we are done for today. So don't forget, for the students who need the ECTS, don't forget to fill in the answers to the questions on Ilias, and also to put in the evaluation report, your opinion on the talk. And yeah, so if there is nothing else from your side, then we can end up the meeting today. So thanks again, everybody, and I will see you next week.